Okay, so we're going to continue building on what we did last time. So last time we got together, we started talking about work energy. And we talked about the fact that work energy could be a shortcut technique that we can solve some problems that involve speed and position. So work energy was nothing fancier than us starting with Newton's second law, F equals ma, and then integrating that over the path. So that's what we did. And I told you it was supposed to be some shortcut technique. But then think about what we had to do, and it didn't seem that short. So for work energy, we had T1 plus U12 is equal to T2. Or the full way, half m my initial velocity squared, that's T1, plus the integral between the two states of our forces dotted with their displacement, dr, is equal to half m v2 squared. My velocity at state 2. So it didn't really save us a whole lot of work because in order to figure out literally what the work term was, we still had to draw a free body diagram because we needed to get those external forces. And then we could then integrate them over a distance. So today, our whole goal is to make this work term easier. So we want to simplify this. And the way we'll do that is we'll take some commonly found forces. So today we're going to use gravity and springs. And we're going to remove those from the work equation. And instead of having them as external work, we'll set these up as potential energy. We'll have a very quick and easy way to solve for the potential energy from springs and gravity. Now, we can't totally get rid of our work term because some forces we're going to call conservative versus non-conservative. So let me jump a slide here. So our springs and gravity forces, something we're going to call conservative. So independent of the path. I don't care how you take this spring, imagine a spring in your hand, and stretch it. And you did some work to stretch that spring, but then imagine like moving its position all over. Every little bit of work you did to stretch that spring, when you compress it again, you gain that work back because that's a force acting opposite the distance you stretched it. So you can stretch it and unstretch it and stretch it and restretch it and do that over and over and over again, but you really only care about where you started and where you stopped for the work you're doing. So because of that, same thing applies with gravity. These are going to be conservative forces, so we don't care about their path. Conservative forces. So maybe a better way to describe this. Here's my bicycle. I'm pedaling my bicycle. And I've got gravity fighting me. Right? Gravity's pointing down. So I've got some mg acting on my body here for my free body diagram. And as I work my way through these hills along this path, you think about the work that I'm getting, right? So mg is always pointing down. But to climb this first hill, my dr is going up, right? So my force is in the opposite direction of my force is in the opposite direction of my displacement. So when I do this dot product, I end up getting a negative value. But then when I go from the top of the hill back down, now my force I still have that mg, is pointing in the direction of my path. So this one would be positive. So whatever work I do to get up, I lose that amount of work, and then I get that back when I come down the hill, and then I lose it when I go up, and then I get that back when I come down, and so on. So if I don't care if I got it back and lost it, and got it back and lost it and got it back, I only care about, hey, I started down here, and I ended up here at position, say, 2, and this is position 1. I just need to know where I'm going. So you can imagine that for work energy, if I pedaled my way up this first hill, and all these hills were identical, and I had no friction operating against the system, and I just let go of the brakes, I'm at the top of this hill, I would come to the next hill, and then to the next hill. I wouldn't have to do any more pedaling work, because I would be kind of having this alternate, this switching of potential energy I gained from climbing up, then to go nice and slow. Then that potential energy would be converted to kinetic energy. I'd be going fast at the bottom of the hill, then I'd be going slow at the top, fast at the bottom, and then slow at the top. So the energy I have within the system isn't changing. I'm just kind of converting it from potential, like stored energy, versus kinetic, the fact that we're moving our particle, half mv squared. So that's the kind of stuff we're going to play with today. And you can kind of think of that stored energy, the two ways we're going to do it: gravity, moving up, and springs. If I squeeze the spring, it's going to have some amount of energy stored in it. If I stretch the spring, it's also going to have some amount of energy stored in it. So I can trade off between these velocity, kinetic energy components, and potential energy, storing it as a spring energy or storing it with gravity. What we're not going to do, and why we still need to use this work equation, is when we have non-conservative forces. So if you have a motor, this is now not a bicycle, but a motorcycle. We're dumping power into the system as we're gassing it, right? If we have friction acting against us, my wife, when she rides her bike, she gets to the top of the hill and she rides the brakes super slow all the way to the bottom. She's got to pedal herself back up to the top, right? She lost energy from riding the brakes, slowing herself down. So frictional work, work from external sources, such as a pull or an external push or a motor, those are still things that we're going to have to deal with our U-term. But we'll talk about that in a second. So if you have the case where we don't have any external work from non-conservative forces, if your work between states 1 and 2 is 0, aside from gravity, aside from springs, we would have what we call conservation of energy. And in this case, we could write our state equation again for kinetic energy at state 1 plus, this is where I got to be a little more careful with my notation. I'm going to try to draw like a big V for potential energy at state 1, plus work, what we're going to say is 0 for this case, when we have conserved energy, is equal to our kinetic energy at state 2 plus our potential energy at state 2. So in the event that I don't have any frictional losses, I don't have anyone pushing on this bicycle, I don't have a motor dropping in torque, hey, here's what we've got: conservation of energy. So what we're going to do is these potential energy terms, that's what we'll spend today trying to figure out. How do I write these for V1 for gravity, that's a little g, and V1s for springs? That's our goal. If we can write this in a simplified form that actually makes it really easy to solve, that makes solving these problems a lot faster. In the event that you don't have, or you do have some external work that's non-zero, we can rewrite our work energy expression. T1, V1, plus the work between states 1 and 2. Now we'll throw a little NC down there non-conservative is equal to T2 plus V2. So now we throw that little NC, the non-conservative work, because I've taken the work from conservative forces and I've pulled them out into my potential energy terms. And that's going to be one for gravity and one for springs. So really, this is the equation we use. Instead of thinking, oh, is this are we conserving energy or not? I just go with the work energy expression and say, hey, what does my work term look like? Do I have frictional losses? Do I have got energy being dumped in or taken out of the system from some other way? All right, so we've got our new form, and I'm telling you it's going to be easier, but we got to go after these guys. So let's try to figure out what our gravity potential and our spring potential look like. So if we've got gravity acting on this body, we've got mg coming down. That's the only one we're worried with right now. So our force vector would be mg, we'll call it the minus j direction, pointing down, kind of a typical xy system. And if I'm trying to figure out my work here, that's the integral of force dotted with our displacements. Maybe I'm taking this ball and I'm doing that with it. Here's state 2. We started at state 1. So you can kind of think that whole talk I just went through, hey, I went up a little, I went down a little. I went up a little, I went down a little. So the work we're gaining by changing in that y direction, I lose some, I gain some. I lose some, I gain some. I lose some, I gain some. So really all I care about is the starting height and the final height. The position, maybe I got to say R1, x1 in the I plus y1 in the j down here. R2, well, that's a 2, not a squared. x2i plus y2j. This integral becomes maybe a bit easier, right? If I think about what I'm trying to accomplish here, my force, constant value, just mg. My displacement, I'm just changing these two positions. So really I've got force times displacement. My force is minus mg in the I direction. And my displacement, delta r, it's a vector, r2 minus r1. So if I got r2 minus r1, x2 minus x1 in the I, plus y2 minus y1 in the j. All right. I screwed that up. J. So sorry, I screwed up my unit vector for my force. My external force is in the minus j direction, so I quick change that I to a j. But now when I do this dot product, I dotted with j for this x term. It's going to go to 0 because they're orthogonal. So I don't care about that. I only care about the j direction. J dotted with j is 1. So what am I left with? Minus mg y2 minus y1. So this can also be written minus mg y2 plus mg y1. And if I was going to use this in my work energy expression, T1 plus U12 is equal to T2. I'm trying to write this out a little easier. Right? I can put this in here. So what's it going to be here? This is going to be my V1 term, and this is going to be my V2. So this is really like minus V2 from gravity plus V1 from gravity. I can substitute that in. And then you see what we're going to get. T1 plus V1 is T2 plus V2. And in this case, these V's, mg times the y position. That, pretty easy to write. When you compare that to starting with the free body diagram, F equals mg in the minus j direction, thinking about your displacements, integrating it, coming up with an idea of what it's going to look like. Instead, hey, my potential at state 1, mg y. Done. My potential at 2, maybe I put a y1 here. My initial height. Potential at state 2, mg y2. Easy. So for us, the only thing we got to do now is be a little clever in our choice for a datum. So again, I got my bicycle path, right? Maybe my state 1 is at the top of the hill. My state 2 is at the bottom of the hill. I get to pick how I'm defining my y value. So I'm going to make my life as easy as possible. I know I've got to track all these terms, but with a clever choice of datum, I can set one of these to 0. So I could pick a datum at the top. I'll call that A. I could pick one at the bottom. That's B. I could pick one in the middle if I hated myself. That's C. Right? Okay? Let's try to write out what this would look like then. T1, V1, T2, V2. You're given some initial velocity at 1, so maybe that's known. But now your V1 term. How are you going to go about writing that? V1 mg y1. So I could do this from datum A, and I could measure off of this line. So if I used A here, my V1 would be mg, my y1 value would be 0. I don't have to worry about potential energy at the top of the hill because I'm picking that as my 0 point. For B, I'd have mg, if my datum was at the bottom of the hill, mg, and now my y1 value is, let's call this 0, 1, and 2 feet. Now it's 2 units, or however many feet it was. If it was C, and for some reason I picked the datum to be the middle, now my y1 value is 1. So do the same thing for V2. mg y2. And I've got A, I've got B, and I've got C. So at position 2, my distance from datum A, mg minus 2. I've gone down 2 to get there. My position at B, I'm sitting on that datum now. mg 0. For C, to 2 is minus 1. Why did I do all that? To tell you that it doesn't matter which one you picked. Overall, you think about what you're going to have here. Maybe let's pretend our initial velocity was 0. I'm going to try to write my velocities now kind of like a little script V. I'm not good at it, but I'm going to try. So my initial velocity falls away. So if I'm with respect to datum A, I've got my potential energy, in this case, is going to be 0 for V1, because that's my mg 0, so that falls away. And then at state 2, I've got half mv squared. So half m little v2 squared plus mg minus 2, my v2. So this is a negative value for v2. So you think I could just move it to the other side and make it positive, right? So what I get is some positive velocity from going down there. Positive of 2 units when I take this piece, which is negative, and I scoot it to the other side. If I flip that and did it the other way, I'd have datum B. I'm measuring from the bottom. mg y1 already is positive 2 on this side. And then for v2, 0. So half mv squared is equal to mg times 2. I get the same result. And then if I did it the funny way, I'd have 1 over here, minus 1 over here. 1, plus it's minus 1 minus, I get 2. It all will work out based on how you pick your datum. My brain tells me, hey, pick a datum where you're zeroed out at the bottom. And then up is positive. Like that, to me, just seems easier. You guys do you. And pick one that is going to give you an immediate advantage. You can at least cross out one term to be 0. That tends to make life a little easier. Those are my 2 words of wisdom. All right, thought experiment time. I got a steep hill. Theta steep. I got a shallow hill. Theta not steep. I realize shallow and steep are the same letter. I've got a little car. I'm going to let them go down the hill. This is the exact same height, perfectly drawn, h. Who's going faster at the bottom of this hill? Tell your buddy what you think the answer is.
Yeah, I guess one will like accelerate. It is crazy. That's what I'm saying.
Okay. You've all got your answer. When you look at this thing, without even thinking engineering at all, what did your eyeball tell you? A or B? Which one's faster at the bottom? Yeah, your eyeball's like, dude, A is way faster. I'm going on a super steep hill. Of course. And then you start thinking about it. You think, okay, well, maybe initially I was not moving. That's 0. My datum's at the bottom. That one's 0. So I got a mgh and a half m v squared, right? Like, hey, I don't care. Both the same. All I'm doing is moving a height. So at the top or the bottom, it shouldn't matter. It should be going the same speed. Kind of, right? But then we got this bugger, friction. So if there was no friction, it wouldn't matter. You know, picture yourself skiing. You're swooshing down, double black diamond, super steep. At the bottom of that hill, you're going fast. Then you got like a little green run, kind of cruising along. You're going slow. You know, that friction matters. So if you think about what the non-conservative part is, so it wasn't like there wasn't an answer to this question, right? I didn't tell you if there was friction or not. So no friction, don't matter. Friction matters. So if I got friction here, I got mg, got normal, I got a frictional force fighting us. I got some angle theta here. My frictional force the frictional force is going to be related to the normal force. So I got to figure out my normal force first. So I got to look at mg cos theta and think, okay, what part of that is rotated in the normal direction? Multiply that by mu k. That's mg cos theta. And I'm going to call this in the little I direction. My displacement, so whatever d is for my hill, starting here down to the bottom. What is that? So if I say sine theta opposite over hypotenuse, h over d. D is my displacement that this thing is operating on, so u from 1 to 2, non-conservative, is the integral of my frictional force, dotted with dr. My frictional force looks a little funky, but it's on a linear slope, so it's constant. So this integration just becomes a multiplication. Mu k mg cos theta I dotted with d, which is h over sine theta in the I. Hey, the amount of work, mu k mg h. I don't like cotangents, so tangent. All right, well, maybe this isn't that super obvious either. But if you know what tangent looks like, so tangent of 0, sine over cosine, 0. The work is a lot. So when this thing is super, super flat, there's a lot of work from friction. Tangent being sine over cosine. If it's super steep, approaching 90 degrees, now I've got about 1 over some small number. This becomes big over little. This becomes really big. Tangent on the bottom really big. Work really, really small. So here I've got very little work from friction. Probably the more intuitive way is to look at it and say, hey, this is a long slope. Ooh, I turned the power off. Oh, nobody wanted to see that. The whole recording is going to be screwed up. I'll start from the beginning. You guys just wait. All right, I'm back. All right. Maybe an easier way, the intuitive way to think of it. The steeper this slope, the smaller the normal force. The less of that force that is being pushed into the hill. The smaller the normal force, the smaller the friction. So your F term is little. So it's little, and the steeper the curve, the shorter the displacement. So little force and a short hill, that makes a little work. Big force plus a big long hill, that makes big work. And our friction, one thing I screwed up here, guys. No one called me on it. My frictional force is in the minus I direction. So work from friction, pretty big deal here, actually. The work from friction is taking energy from the system. Like friction is a little energy monster, right? It's like slowing us down. So we're going to be going slower at state 2 because of friction. Friction is not adding energy into the system. All right. This guy again. Recap what we did last time. Talk about how easy it is now. So last time we did this problem, we got together. We drew a tension off the ball. We drew mg coming down, so we had T going up. Mg coming off the ball. Hey, we said we used the polar coordinate system. U hat r, U hat theta. We said the tension's not doing any work because it's always perpendicular to our motion in theta. We said our weight is doing work because it's in that r direction. So, our weight is doing work because some portion of our weight, mg, is in the theta direction. That makes more sense when I say it that way. Right? This is the leg of my mg that's in the theta direction. So we did the integral, but we had to come up with things. But now what we know is, hey, I don't have to think about the path that this guy's riding on. I don't have to use polar. All I need to figure out, how high did that ball move up? T1, V1, T2, V2. Right? So maybe I was given some initial velocity, V1. Maybe I picked this as my datum. So if I pick the bottom as my datum, that's a state 1. This is state 2, where it's swung up to. We lose this guy. Maybe the question asks us, how fast are we going at state 2? V2 equals question mark. I think that's what it did. We just need to figure out, to get that, mg h2. This is h2. How high do we come up? That's the only thing that we really need to solve this problem. So I've got this whole chord as length L, and this is h. This down here is h. What I need to figure out, I want h, I need to figure out what this piece is. This piece that I'm trying to draw in green. That's theta. So we remember that this guy is L. So this little one that I just tried to draw in green, that's the cosine leg of L. L cos theta. So if I look at what I've got here, my height, L, is equal to these two pieces. H plus L cos theta. So this full leg is made up of the sum of the two pieces. This H2, which I've called it before, so I'm going to stick a 2 back on there. H2 is L minus L cos theta, or L times 1 minus cos theta. Done. Really simple equation we get to use. V2 is just mg h2. So mg L times 1 minus cos theta. No integrals, no polar coordinates, no dot product vectors, just some good old-fashioned geometry. Not too hard. So this is where, using these potential energy equations, we're going to get a little bang for our buck. It's going to make life hopefully easier for us. All right. The other one we want to look at springs today. So we just did potential from gravity. Now we want to do potential from springs. So what do we got here? I got a little spring. And I can pull on this spring, I can push on this spring. But the spring force, I just set up a little coordinate system and anchored at the bottom. So I put a little coordinate system on here at my spring. My spring force is always going to be pointing in this radial direction. It's always going to be aligned between the ends of the spring, pointing back. So if I try to draw this out, like maybe I have a case where I've stretched in the positive u direction. I've made this spring longer. So now I've got some tensile spring force. This is F spring, because we've stretched it. So if I try to write this out for tension, my spring force would be minus my spring force in the u hat r direction, because this is pointing in the opposite direction of r. Trying to go back home. If I squish this guy down and made this spring shorter, I'd have a spring force, but now it would be in compression. That's my C. Compression. So now my F of my spring is going to be in the u hat r direction. F of the spring, u hat r. Then you got to think about, okay, what's the work we did to do these? So if I have a spring force in the opposite direction of u hat r, my displacement is in the positive direction, right? So I'm stretching it to make it longer. This would be positive, this one would be negative. If I did the opposite, compression, my spring force is in the positive direction, but my dr, I'm making it shorter. So my dr is actually in the minus r direction. So the amount of work is going to have that same sign, right? So one, I'm going to have a negative force in a positive direction. In the other, I'm going to have a positive force in a negative direction. That's just going to set the stage for what we're doing in a second. All right, taking you back to statics. The force of a spring, we define that. Some spring constant K times L. In this case, we could say K times R minus the initial length. Just our change in length. I've only got 10 minutes, so I don't really want to do this. So if I plug in my integral from 1 to 2, for my spring force, let's do the tension case here. I got minus K R minus L0 in the R direction, dotted with dr. This is dr in the u hat r direction. Our dot products can get rid of the vector. Now it's going to be a scalar. I got to integrate this guy with respect to r. So I got minus K r squared over 2 minus L0r, evaluated at R2 and R1. This is what my work is. you can go ahead and plug in R2 and R1. You got to do a little bit of tricky algebra that I don't want to do. And then we'll get to what our U value is. Minus K over 2. And we've got, I'll do it this way. R2 minus L0 squared minus R1 minus L0 squared. This first one, delta 2 squared. This second one, delta 1 squared. Just our change in our initial spring. So how much is our spring initially? That's a squared. How much is my initial spring stretched or compressed? And then at state 2, how much is my spring stretched or compressed? So from this, we can pull our potential for springs, half K delta squared. Interesting thing is that I don't care whether I'm compressing the spring, making delta smaller, negative value, or if I'm stretching it. The squared value is just going to be energy, you can think of it as energy stored in that spring, right? This is potential energy stored up in that spring. So you've got a spring, you're stretching it, you're holding it here. Yeah, there's energy stored in there. If you got that same spring and you're squeezing it the same amount, there's energy stored in there. The same amount of energy. And we don't even know. Is it stretched or is it squished in this sense, right? We just know that it's storing energy, and that's all we need and all we care about. Okay. Example time. I brought back my launcher. I spent minutes making this thing, so I'm going to get my use out of it. So we used this launcher for projectile motion in this very sophisticated device that I created after hours of engineering. Looks like this. It is a tube with a spring in it, and it's shooting a projectile, right? So we did some stuff for projectile motion where we had some angle theta here, and we tried to figure out where it was going to land, or maybe we tried to figure out how to maximize this distance as a function of theta. Today, I care more about the spring part. So let me just quickly do the projectile, a little bit of it, all that we need, and then we'll move on to the interesting part. So I'm trying to maximize my distance. We could say that this final location for our projectile, V0 cos theta t, this is our final position as a function of time, an initial velocity. We had a y final position, so minus g over t, minus g over 2t squared, plus v0 sine theta t, plus a y0 term, which we're going to set at 0. We could say at its final position, y final is 0. It's hit the ground. Solve for t. Plug back in here. And what we get, my final position is 2 v0 squared over g cos theta sine theta. Okay. Who cares? We don't. What we care about is that my final position is proportional to my initial velocity squared. That's all I care about. How far this thing is going to go is a function of constants, if I'm holding these constant, times velocity squared. That's what we want to do. So today, my launcher has multiple positions. So initially, if you had your X-ray vision, my weapon is sitting right here-ish. I have a push rod where I push this thing back, and then I can cover up this hole, hole 1. Or I can cover up this hole, hole 2. I can pin my projectile in here, and I can let go. So I can launch this thing at different amounts of spring compression. Right? So I can either compress it to delta 1, which is like an inch, or delta 2, which is like a little more than an inch. So what happens when I compress the spring more? From what we know of energy, I'm storing more energy in that spring. So then when I let it go, that potential energy should be converted to kinetic energy. So if I squish the spring more, I should get more velocity out, right? That's what this is telling me. So I've got T1, V1, T2, V2. So if I think about my positions, I have a little bit of freedom here. I'm going to say position 1 is compressed. I've got this spring squished down, and maybe I'm looking like this. Right? So I have T1 is 0. My initial velocity, I got this thing compressed and locked. My spring, V1, half k delta 1 squared. At position 2, that'll be after my spring has extended back to normal and this thing has got all its energy converted to kinetic energy. So half m v2 plus, so state 2 is uncompressed, v2 is 0. Because now my spring isn't squished. A little part that I'm going to sweep under the rug here. Right? I am moving up some height in gravity. Right? I got some little h here. So I will have v2 of the spring, 0, but I will have some v2 from gravity. Because I'm only moving up a few millimeters, let's consider that small for now. But certainly, all you would have to do to figure that out is a little triangle with my angle. So what do I got here? If I pretend this is small for now, just so we can neglect it, I've got that my delta squared is equal to my velocity squared, some proportion. Delta is proportional to, or delta squared is proportional to velocity squared. So if there are squares that are proportional, I can just take the square roots, and they are proportional. Delta is proportional to velocity. So if I change my spring stretch by a factor of 2, I'm going to change my velocity by a factor of 2. And then if I come up here, I change my velocity by a factor of 2, I'm going to change my launch distance by a factor of 2 squared. So 4. Let's see how dangerous this gets. So what I've got here is my delta 1, 23 millimeters, delta 2, 33 millimeters. So my delta 1 oh no, all this hype, and now I don't know where part of it is. Oh, I got it. Fear not. So my delta 1, I just pick some random, perfectly locked angle, and I shoot this guy. Oh, so wimpy. Whoever left their water bottle here, it's now part of the demo. Call it right there. And if you can think about what I have here is my ratio of delta 2 to delta 1. Now if I go to my super blaster distance of delta 2, I've moved this up by a factor of like 1.4. But I know that my velocity then will be moved up by a factor of 1.4. So my displacement should be moved up by a factor of 1.4 squared, which is about 2. So just knowing that I've moved this guy a little bit, we should shoot it 1.4 times faster, which should go about 2 times farther. Whoa, way more than 2. Okay. No. Maybe my calculations aren't perfectly accurate, or maybe my first blast wasn't accurate. But kind of cool that if all you know is the spring stretch, you can figure out a whole bunch of stuff. You could figure out spring constant. You could figure out how dangerous this thing's going to be in your office when you're making it. Like, I got to shoot it from here. How far do I think it's going to go? Pew! Oh, that's one. Pretty repeatable, actually. So, kind of a fun example. I'll see if I can bring this thing back for a couple more times. If anybody wants to shoot it and get dangerous, you can come on up.